You ask a chat model about the cancellation terms for SKU1042 in your company's product catalog. It answers immediately. If SKU1042 has a 30-day cancellation window with a 15% restocking fee. It's confident, specific, made up. The model has never seen your catalog. It does not know SKU1042 exists. The catalog is not in its training data, and even if it were, the data inside your company changes every week. This is not a prompt engineering problem. It is how language models work. RAG is how you fix it. RAG stands for retrieval-augmented generation. 3 words, 3 steps. You retrieve relevant information from your own data. You augment the model's prompt with it. Then you generate the answer. The model never memorizes your catalog. It does not have to. It reads the relevant page right before it answers. That is the entire idea, and the rest of this video is the mechanics. First, you prepare your data. Take your product catalog and split it into chunks. Small enough that the model can embed each one cleanly, big enough that each chunk still carries meaning on its own. There is a whole episode later in this series on chunking strategy. For now, a simple recursive split is fine. Each chunk is a candidate page the model might need to read later, including the page about SKU1042. Each one carries its source file and where it sits in the document. That metadata is going to matter. Step 2. Turn every chunk into a vector. A list of numbers that represents the chunk's meaning, not its words. 2 sentences can share no words at all and still land close together in vector space if they mean the same thing. That proximity is what will make search work in a moment. Each chunk is now a coordinate in a high-dimensional space. The dimensions do not have human names. The model learned what to measure. The page about SKU1042 lives in this space. It just has not been picked yet. Step 3. Store every vector. Chroma, Pinecone, Quadrant, they all do the same job here. They index your vectors so you can search them in milliseconds across hundreds of thousands of chunks. Think of it as a library where the shelves are organized by meaning, not title. You never browse it. You ask it a question and it knows where to look. After this step, the page about SKU1042 is somewhere on those shelves, waiting to be found. The user asks a question. That question goes through the same embedding model as the chunks. Same coordinate system, same units of meaning. Now the question is a vector that lives among all the chunk vectors. The database returns the chunks whose vectors sit closest to it, cosine similarity, top 5. And here, the chunk about SKU1042 climbs to the top with a similarity of 0.80. That score looks confident. We will come back to it. The top 3 chunks go into the prompt, not all the chunks in the database, not even all 5 retrieved. 3 carefully chosen pieces of context placed directly before the question. The model reads them the way you would read a briefing note before a meeting. It does not guess from training. It reads what is in front of it. And now, for the first time in this video, the prompt physically contains the page about SKU1042. Same question, same model, different result. The cancellation terms for SKU1042 are right there in the context, and the model quotes them with the source attached. Look at what just happened. The model did not learn your catalog. It borrowed the right page for one answer. That is RAG. Retrieve, augment, generate, and the model only ever sees 3 pages at a time. This is naive RAG. For this question, it works, but you have not built it yet. Next episode, we build this exact pipeline from scratch, load the catalog, split it, embed it, store it, retrieve from it, and answer with citations. After that, we come back to the uncomfortable part hiding in scene 6. That 0.8 similarity score looks trustworthy. It is not always relevant. That is where re-ranking starts.